Hello again, physics friends. This is a very exciting moment because we now have all of the pieces in place to understand that gravity and a gravitational field affects the rate that a clock will tick. And what we'll see is that that effect, called gravitational time dilation, can be used to understand and explain the physics behind the twin paradox and why Bob's clock appears to jump forward in Alice's frame when she turns around at Sirius. We have a little mnemonic to remember all of our relativistic effects, like rear clock set ahead, moving clock ticks less, and moving rod is short. The corresponding mnemonic for gravitational time dilation is a lower clock ticks less. So what do we mean by a lower clock? Well, I have a little diagram here to show you. We have two clocks, and they're each at different heights relative to the Earth. So we have the Earth right here. We have a clock that's low to the ground and a clock that's higher up. And I've indicated here the fact that there's a gravitational attraction towards the Earth. So these clocks are in a gravitational field. When we say a lower clock ticks less, we mean the one that's closer to the Earth is going to tick more slowly than the one that's higher up. Now, you might be wondering, well, how on earth can the strength of gravity affect the rate that a clock ticks? And to see that, we're going to use the principle of equivalence. And you'll remember that the principle of equivalence tells us that we can replace the gravitational field with an acceleration. So I'll draw a series of diagrams showing a rocket ship that's accelerating, and we're going to talk about the readings on two clocks in this accelerating rocket, and then we're going to tie that back to the readings on these two clocks that are at rest in a gravitational field. Okay, so here we have our rocket. It's out in deep space. There's no matter around other than the rocket, so there's no gravitational influence on the system. We have a clock at the tail and we have a clock at the nose. And the game we're going to play is we're going to have the clock at the tail release two photons. Once when the clock ticks 0, and once again when it ticks 1 nanosecond. So these two photons are going to be emitted 1 nanosecond apart. Okay. Those photons are going to be shot up towards the top clock. Okay. And our goal is to then figure out what is the difference in time of the arrival of those two photons at the top clock. Okay. If the ship was in an inertial frame, meaning not accelerating, then those two photons would emerge 1 nanosecond apart at the bottom clock, and they would both travel the same distance at the same speed, and therefore they would also arrive 1 nanosecond apart at the top clock. But after we launch these two photons, we're going to turn the thrusters on so that as the photons are traveling, the ship is accelerating. Okay? And I should point out that these clocks are attached to the ship. So when the ship accelerates, so do the clocks. Okay? So what that tells us then is we have these two photons that are 1 foot apart because they were emitted 1 nanosecond apart in an inertial frame. But then these two photons have to chase a clock that's running away, and running away at a faster and faster rate because of acceleration. What that means is the two photons will arrive more than 1 nanosecond apart as measured by the top clock. And what we're going to do with that information is tie that back into the lower and higher clock in a gravitational field using the principle of equivalence. So that's kind of an outline of where we're going to go. What I'm going to do next is draw this diagram 3 times, showing the emission and then the travel of the photons and the arrival of the photons. Okay. The first thing, though, that I'm going to do is be very careful in how I identify my frame of reference. Okay. I can't just say the rocket frame because the rocket is going to be accelerating, and if the rocket accelerates, it is not an inertial frame. And we want to do our analysis in an inertial frame so that we can use all of the tools of relativity that we know and love. Those are valid in an inertial frame. So the frame that we're going to use is what I'm calling the original inertial frame of the rocket. In other words, this rocket, say, was at rest in this frame when it emitted the two photons. As soon as that second photon has been emitted, this rocket starts accelerating. okay? But we're going to keep the frame the same as the frame in which those two photons were emitted. So in the very beginning, in the first instant of time, the rocket is not going to be moving because it's in its original inertial frame when it emitted those photons. But its thrusters are on. So I've drawn the thrusters as on, even though it's not yet moving. So it's starting to move. It has an acceleration, but it has no velocity. So in this diagram, there's an upward acceleration, but there's no velocity for the rocket. In subsequent pictures, there continues to be an upward acceleration, but now the rocket will be moving, and so will the photons. So let's see what the next picture is going to look like. Okay, we have our new picture, and we see the rocket continues to accelerate, same acceleration, a uniform constant acceleration up. The speed is now not zero, so now the rocket's moving and has risen from where it used to be in this frame. We still have our two photons, which remember were emitted 1 nanosecond apart, so they're separated in this frame by 1 foot. As they travel, their speed in this frame is the speed of light, so they continue to be separated by 1 foot, as if the rocket were not there. Okay? The acceleration of the rocket has no impact on the motion of those two photons. So they continue to be 1 foot apart. Okay? Let's see what happens in the next picture. And in the next picture, I'm going to draw the first photon arriving at the top clock. Okay, a couple things to point out in this third diagram. Number one, because we continue to accelerate, and maybe I'll be really explicit about that, I'll indicate that we continue to have an acceleration, which we also indicate by the fact that the thrusters are on. That means our speed is growing. And if our speed is growing, then the distance traveled by the rocket from in one pair of pictures is going to be different than in the next. So in the first picture, we're down here. We rise up a little bit to get to our second picture. We rise up more to get to our third picture because our speed is increasing. That's one thing to notice. The other is that now this first photon has arrived at the clock. Okay. Now our photons are 1 foot apart, as they always have been, because they were emitted 1 nanosecond apart in the original inertial frame. So if this top clock, let's say this top clock has a job, and its job is to register the arrival time of the first photon and arrival time of the second photon and report that time difference. Okay? Well, this first photon has arrived. Okay? Now think about this second photon. In order for it to arrive, it has to close this gap of 1 foot, but it's chasing a moving target, right? This second photon is going to have to travel more than 1 foot to make it to the top clock because the top clock is currently 1 foot away, but it's moving away from the photon. Okay? So what that tells us is that this second photon is going to travel more than 1 foot, so more than 1 nanosecond will tick off on this top clock. And that really is our main result, which is that in an accelerating rocket, the nose clock ticks off more than 1 nanosecond, while the tail clock has ticked off exactly 1 nanosecond. So that's what happens in an accelerating rocket, far from any gravitational influence. But the principle of equivalence, right, tells us that we can replace the gravitational pull by an acceleration or vice versa. So the problem that we just analyzed is equivalent to the problem that we wanted to solve, 2 clocks at rest in a gravitational field of the Earth. The principle of equivalence tells us that these 2 clocks must behave in the same way as these 2 clocks that are on the rocket. And so that gives us the main result, that the lower clock ticks less. In this case, the clock close to the Earth ticks less than the clock further from the Earth. In the accelerating frame, that is the tail clock ticking less than the nose clock. So there you have it. Using the principle of equivalence and a little bit of general relativity, we learn that gravity actually affects the rate that clocks tick. And so now we have the tools to understand why Bob's clock advances so much as Alice slows down, turns around, and speeds up when she reaches Sirius. In other words, now we have some physical intuition and understanding for how to resolve the twin paradox. And indeed, in the next video, we're going to use gravitational time dilation to analyze the twin paradox and look at what happens as Alice slows down, turns around, and speeds up. So we'll use this principle of equivalence to understand that her acceleration is equivalent to a gravitational field, and that we know that a lower clock ticks less. So we're going to figure out, is Alice's or Bob's clock the lower clock in that problem, and which one is going to tick less. And that's going to help us resolve the twin paradox. So we'll come back to the twin paradox in a future video, but right now I want to show you some experimental evidence for gravitational time dilation. It's one thing for me to draw a picture and say that clocks tick at different rates depending on where they are in a gravitational field by this principle of equivalence, but if that's true, then we should be able to measure that effect. So let's see what has been done on that front. To set the stage for the experimental evidence, let's just make sure we're all on the same page about what the expectation is, right? So we showed using a rocket that's accelerating that the time ticked off on these two clocks will be different. And we use the principle of equivalence to connect that to a situation like the following, where we have the Earth in a gravitational field, and on the Earth we have a tower with a clock up high and a clock down low. And the claim is, for gravitational time dilation, that the low clock ticks less. And you can show with a direct calculation, we're not going to do it here, but you can show that the amount of time that the high clock ticks is related to the amount of time that the low clock ticks with this factor 1 plus gh over c squared, where g is the gravitational acceleration near the surface of the Earth. And this is valid for short separations and small masses, like we see on the Earth and for a tower. What we'll see in a little bit is that this number ends up being very small, a couple parts in 10 to the 15. So what that tells us is that th and t naught are going to be pretty close to identical with each other, but they are going to differ at a few parts in the 10 to the 15 level. So has this test been done, or has a test like this been done? And the answer is yes, and not recently. It was done a long time ago. Before I show you the specifics of the test, I'll just share with you this photograph that I took while I was walking through the basement in one of the laboratories in the physics laboratories at Harvard University called Jefferson Lab. And as I'm walking down in this kind of dark hallway where there's vats of liquid nitrogen and compressed gases and random other things, I noticed a sign on the wall. And when I looked more closely at the sign, this is what I saw. It's a plaque commemorating an experiment by Pound-Rebka, two physicists, that in 1959 they measured this gravitational time dilation by looking at the frequency of light and how that changed as a function of height in the tower. So we'll see exactly what that means in a moment. But there's this nice local connection in the Boston area to tests of general relativity and specifically to time dilation. So here's a little bit of the geometry of the problem, right? This is Jefferson Lab at Harvard University. And Pound-Rebka had a vacuum tube that went from the penthouse all the way down into the basement, which is where that plaque was located. And the change in height between those two locations, or the difference in height, is 22 meters. Okay. So if we come back to that expression I showed you before about the difference in the ticked off time on these two clocks due to the gravitational field, there's this term, this gh over c squared, and little g is the acceleration due to gravity near the surface of the Earth, which is about 10 meters per second squared. And for a height of something like 20 meters, this term gh over c squared is very small, because c is enormous compared to this quantity gh. So c squared is enormous compared to that quantity gh. And that term ends up being about 10 to the minus 15. What does that mean? Well, that means that the high clock is going to tick more times than the low clock, but over the course of a whole day, that difference in number of ticks will be less than 1 nanosecond. Okay. And yet, Pound and Rebka were able to devise an experiment where they could effectively test and measure this effect, which is really phenomenal. So this is a very high precision measurement that allows them to measure a part in 10 to the 15 difference in the rates the clock ticks up high and down low. And they use for their apparatus a radioactive isotope which emits a photon of a very well-known frequency, and they can measure that frequency very well. And they know what it is at emission, and they know what it is at the detector. Okay, and they can look for a difference in frequency. We can kind of think of frequency as a ticking clock, right? It's oscillations per second. So frequency and time are kind of inversely related to each other. Time per tick versus ticks per time. And they did this experiment, and they actually measured this quantity, and they did so with an accuracy of about 10%. And in subsequent experiments, they improved. Well, it wasn't exactly the same two people, but the experimental accuracy improved to about 1%. So these are just really beautiful measurements that confirm a rather bizarre aspect of general relativity, that gravity affects the rate that clocks tick. On a related kind of interesting side note, one of the projects I work on is called Apollo. It's the Apache Point Observatory Lunar Laser Ranging Operation. And in that experiment, we fire laser pulses from a telescope on Earth to the moon, and we measure the time it takes for those light pulses to go from the Earth to the moon and back. So we're measuring the Earth-Moon distance and mapping out the geometry of the orbit of the moon and asking, can general relativity explain all of the features of the lunar orbit or not? Or is there some evidence for physics beyond general relativity? In other words, is our understanding of gravity accurate enough, or do we need a new model for gravity? In order to make our measurement, we use a GPS clock, and we also use an atomic clock. Both of those clocks are located at the mountaintop at the Apache Point Observatory. So we actually have two physical clocks next to each other side by side, and they're connected by a cable. So we can monitor the difference in time between these two clocks, one atomic clock and one GPS clock. Although the GPS clock is located at the mountaintop, the GPS clock, so the global positioning system, that GPS clock is dictated to run at a rate as if it were at sea level, or something that's close to sea level. So although we have two clocks side by side with each other on the top of a mountain, one of them, the GPS clock, behaves as if it were at sea level. The other clock, the atomic clock, just behaves as if it were where it is, which is at the top of the mountain. So although these two are side by side at the mountaintop, we basically have a configuration like this. And so we can ask the question, is it the case in our experience that the atomic clock, which is at the mountaintop, ticks more than the GPS clock, which behaves as if it were at sea level? Okay. So if that were true, then we would expect the atomic clock's reading to get larger at a faster rate than the GPS clock reading. And indeed, this is a plot of the atomic clock reading minus the GPS clock reading in nanoseconds over as a function of day. So this x-axis here is time and measured in days. So this is essentially 1 year of time. And this is the difference in time between the clock readings in nanoseconds. So we can see that over the course of about 1 year, the difference in time between these clock readings increased by about 5,000 nanoseconds. So the black dots are the data, and the dashed curve represents the theoretical prediction given the equation that we've seen before, which is exactly the same equation that Pound and Rebka were working with, except instead of a 20-meter tall tower, we have a 2,800-meter tall mountain. So the effect for us is going to be 100 times more substantial than it was for Pound and Rebka. So it's quite kind of nice. We did not build this Apollo experiment to measure gravitational time dilation, but along the way we realized that we had the ability to do so. And here's some actual data from that experiment. Okay, so just to refresh a little bit and to summarize, we have shown that the principle of equivalence can be used to tell us that gravity affects the rate that clocks tick. And we've shown that there is experimental evidence that confirms this rather bizarre and interesting phenomenon. Now that we have this under our belts and we understand gravitational time dilation and we understand why gravity affects clocks and also that an acceleration can affect clocks, we're going to use that information to gain a deeper understanding of the twin paradox. So that's coming up in the next video. Until next time, my friends, stay well and be good.